Okay, so we first see relationship between 3D computer vision and robotics, and some basic definition of robots, motions, 3D rotation, and forward inverse kinematics. Maybe some of you guys know the term called physical AI is now getting popular these days. NVIDIA tries to accomplish this kind of physical AI, and the main component of physical AI is robots. We have virtual, agent AI. We have ChatGPT, Gemini. We have very good AI system in virtual space, but in physical space, in real world, the space we are living in here, we do not have such kind of advanced AI system. And the physical AI, the goal is to introduce this kind of very highly advanced AI system in our physical world. And the main component is robots. Of course, there can be many other hardware like autonomous driving, but robots is one of the main components for this physical AI. And robots, maybe some of you guys know, robots have been studied for decades, of course before AI boom. One of the main, this shows the early approaches for robots. But there are many bottlenecks. Robots was too difficult, but one of the main bottlenecks for the robots was perception. At that time, computer vision was not mature at all. Actually, computer vision, when I entered graduate school, computer vision was not very major topic. It was a little bit minor topic actually. And many people did not think that computer vision could be robust as these days. Because at that time, deep learning has just started to be introduced, and many people did not think that computer vision could be robust and stable as these days. And these days, computer vision is becoming mature so that robots are gaining attention again. So researchers, especially robotic researchers, hope now robots spring is coming. So the combining advanced computer vision algorithms, generative AI, multimodal reasoning, robotics are getting forward these days. COR, Conference on Robot Learning, one of the most major prestigious robot conference, 2025 was held in Seoul actually, in September. Attended, this is the picture of the COR. Actually much less people than Civic Conference. Civic Conference, there are so many people, but robotics community, the community is growing very rapidly. And many researchers, computer vision, computer graphics researchers are trying to expand research area to robotics, and there are many computer vision graphics researchers in COR actually. And what technology for robots, which top technologies for robots we need to implement. So there can be several components. For sensing means tries to perceive what is happening. We humans have five sensors, right? We have eyes, ears, we have five sensors. For the eyes, vision, computer vision, hearing, speech recognition, touch, tactile perception, smell and taste, chemical sensing, and thinking, maybe LLM, and motion, physics-based robot control. And this is the major focus for remaining classes. Physics-based robot control. For this kind of physics-based robot control, we need to get familiar with forward inverse kinematics, reinforcement learning, and these days, vision language action models. So 3D computer vision, we need to perceive what is happening. Among five sensors, the eye vision sensor has the strong semantic information actually, the strongest semantic information. So the 3D computer vision is actually necessary for realizing robots, realizing natural interaction between robots and our environment, natural interaction between robots and human. In this picture, robot needs to perceive, recognize position and rotation of object. Where is the object and what is the rotation of object? And also when interacting with human, it needs to perceive facial expression, gesture of human, or location of human. We need to perceive all the things with vision algorithm. But especially 3D vision is actually very necessary because robots must know, for example, there are many examples. distance to reach, grasp, and avoid obstacles. Robots are, just moving around and needs to avoid some obstacles, or needs to grasp some targeting object. It needs to distance to reach, grasp, and avoid obstacles. And robots operate in 3D space, requiring full 360 degree of freedom object pose. This is degree of freedom. Position 3D, orientation 3D, so 60 degree of freedom. And 2D images lose geometry, making it impossible to tell size, shape, or orientation. We know this one, right? There's a scale depth ambiguity. Occlusion cannot be resolved with 2D alone. 3D helps separate overlapping object. Safety requires accurate 3D distance to human obstacles. And manipulation needs surface geometry, not just 2D appearance. So that, if you start robotics research, you can immediately realize that 3D computer vision is necessary. Without 3D stuff, you cannot, you can't do, there's nothing you can do. Especially in motion, this kind of motion, physics-based control, all the things are in 3D. Forward, inverse kinematics, 3D rotation, reinforcement learning, it tries to do reward in 3D space. Play model tries to, the joint angle, they are joint, right? They are joint angle, and robot needs to apply torque or force to the joints. And then this kind of force and joints are torque are in this 3D space. So that we need to fully understand the 3D stuff for the robots. And this one shows challenge of robots. You can see there are many hilarious failure cases. This is not, 5 years old video. This is, very recent video. These days, computer vision, generative AI, multimodal reasoning are advanced, but still, these kind of robots have elementary level mistakes. It is hilarious, but at the same time, it looks a little bit dangerous, right? This is very dangerous. Yes. So, we have ChatGPT, Gemini, and they are like human, right? We can have natural interaction between them. We can feel some weird stuff in some cases, but usually having interaction with ChatGPT or Gemini, it gives us good experience, right? But robots is still a very elementary level mistake. It is not doing complicated tasks. It is not assembling very complicated manufacturing stuff. Just walking around or playing soccer, or just showing some demonstrating some jump. This kind of very elementary level kinematics motion. It still fails to do that. So the robots are actually quite immature. So why this happens? We have very advanced AI system, computer vision, all this, we have advanced system. Always the challenge is from data. It is very challenging to collect physically plausible training set in the wild. So physically plausible means physically correct training set in the wild. How can we do that? How can we get physically correct training set? We need to fully attach markers on our body and then capture with very many numbers of cameras. If we can do that, then maybe. But constructing such kind of physically correct capturing devices, capturing setup is very expensive and costly. So in the wild means just daily life. In our daily life, constructing such kind of capturing setup and capturing with such kind of expensive setup is not scalable, right? We can capture some small scene for this special setup, but it is not scalable. As an alternative, people often use these days physics-based simulator like Isaac Sim. This is visualization of simulator. As you can immediately note that it seems a little bit far from our real environment, right? The problem is the simulator consists of two simplified environments. for example, adding realistic assets, like I want to add this bottle to this physics simulator. If I want to add this bottle to the simulator, I need to know exact mass, fraction coefficient, size. I need to add all these kind of physical properties to the simulator. But measuring such kind of physical constraint, physical properties, is also very challenging, and it is not scalable. I mean, we always need to fully measure all these kind of physical properties and then add to simulator. That is not scalable. So it's very difficult. Adding some realistic assets to simulate very difficult. And photorealistic rendering capability is also limited. I mean, even Unreal Engine, this kind of stuff has a little bit lower photorealistic rendering capability. But as you can see, this kind of widely used physics-based simulator, like Isaac Sim, they have very limited photorealistic rendering capability. So that you can see the images are very far from real images. The lighting model, I think they're just a diffusion lighting model, so that there's no specular. I mean, and the environment is very simplified. There is no background. There's no image-based lighting, so that image itself looks like very simplified. So that robots mainly train on this kind of very simplified environment, of course, cannot generalize to real-world environment. As you can see, these robots failed in real environments. So the first challenge is getting physically plausible training set in the wild is challenging and not scalable. So that people use physics-based simulator, it consists of two simplified environments. And this is from lecture 14. We already covered data collection challenges, so that we use multiple types of data sets, multiple studio image, synthetic image, in the wild image. But as you can see, even multiple data sets often have physically implausible 3D human notations. And this one, I mean, if you have this kind of 3D multiple data set, I mean, you might get this kind of 3D human notation. This is, I mean, in terms of only separating human, the 3D human pose is almost the same, but there is a physically implausible stuff, right? This human is penetrating inside of the couch. So there is even we use multiple data sets. We have cameras, but the camera is only capturing visible surface. It cannot capture invisible surface, right? So that multiple data sets, even if we use multiple data sets, we often have physically implausible 3D human notations. So that data collection for these robots is very challenging. And in the wild videos, of course, have much more penetrations. As you can see, this one is also showing physically implausible outputs. The foot is hovering on the floor. There is no contact between foot and floor. And then the hand is penetrating inside the floor, as you can see. Another thing is that embodiment gap. Robots and humans, we have different shapes, right? Robots and humans, of course, they have different shapes. We usually have average height might be 170 centimeter, maybe average height for all humans, maybe. Robots usually have much smaller size. Even humanoid, they usually have 120 centi, maybe. The size is also very different. And for hand, this shows the embodiment gap for hand. There are many types of hands in robots. 2-finger hand, 3-finger hand, 4-finger hand. The reason why, of course, if we can design 5-finger hand, that might be better, maybe. But the problem is that controlling 5-finger hands properly is very difficult. So that in many industry, people just use 2-finger hands because it is easy to control. Or maybe if we can design 10-finger hand, maybe. We are not sure what is the optimal design, but robots, if we can design robots that like human, they might be good, but we do not know that is optimal choice. Some different embodiments of robot might be optimal. We do not know what is the optimal embodiment of robots. Anyway, robots and humans have embodiment gap. Humanoid size or the number of finger or the ratio of upper body and lower body, there are many embodiment gaps. So that if we have large amount of human data, it is not easy to transfer to robot case. And the third challenge is that robots should move in a physically plausible way. even tiny mistake can make entire fail. So you can see, you watch the video, right? Robots just fall and just crash on the floor. There might be a very small mistake, maybe, but it can make entire fail. And actually, that can make quite severe safety issue, right? I mean, robots and humans can crash together. There can be very dangerous situations. Computer vision, computer graphics, and AI, they are in virtual space, and they are not following physical law, actually. They're just generating some visually plottable stuff. They are not governed by physical law. So that we can get some, there can be, in some cases, they violate physical law, but we do not matter. I mean, it doesn't matter. As long as it's visually pleasing, it is good. In virtual space, the goal is visual pleasant, right? We're not interested in physical law. Of course, if it can follow physical law, the visually it might be more pleasing, but it is not strictly following physical law in the virtual space. So it is okay to have some mistakes, some physical mistake is okay. And as long as we have the same code, all experimental results are reproducible, right? But Robots are very different. Actually, it is hardware. Hardware makes a big entry barrier. I'm not very expert to hardware. Maybe mechanical engineers might be expert to hardware, but many computer science engineers are not expert in hardware. And there are many more things to consider, like a temperature robots. In some day, robots is too hot, temperature is too high, so that it cannot do. But next day, tomorrow, robot temperature goes down, and then it can do the same thing with the same environment. Only difference is the temperature of robots. That happens quite a lot. So that there can be many things to consider in hardware and physical space, so that implementation and experiments are way more difficult than this kind of virtual space experiments. So the reproduce of this kind of experimental result is not very easy in hardware side. So 3D computer vision is one of the necessary techniques for robots, and robots are still immature. And there are many remaining things we can do. And actually, that is the why many researchers are expanding to robotics, including me. And challenges are physically plausible and diverse data. It's very hard to get embodiment to gap between human and robots, and hardware entry barrier. And then let's proceed to 3D rotation. We need to first define what is the robot motion, what is the basic component of robot motion. So we learned 3D translation, 3D rotation, right? 3D translation, it usually represents this kind of global locomotion, the global trajectory of robots, how long the robot moved. 3D rotation actually much more important and difficult. We have joints, right? This robot has here joint, and joint. It has 3 joints. We have joint here. We have wrist, elbow, shoulder, hip, knee, ankle. We have also human have joints. And for each joint, there can be 3D rotation, so that we can rotate our human body. Also applicable to robots, an essential part to define robot motion. So the problem is that 2D rotation is very easy. This is high school math, right? Just a single scalar, the single theta is enough. And just a 2D rotation matrix, and 2D rotation, there is no ambiguity. It is not very difficult. But the 3D rotation, although we only add 1 dimension, things are totally different. It is two-way complicated, actually. Much more complicated than 2D rotation. And for the 2D rotation, we only use a single scalar to represent 2D rotation, right? We use just theta. The 3D rotation, there are many representations, unfortunately. It is also very similar to 2D and 3D representation, right? 2D, we only have image representation, but on 3D, we have mesh, volume, point cloud, implicit, or 3D Gaussian. We have lots of representation. It is very similar. For 2D rotation, just single scalar, but on 3D rotation, we have lots of representations. Rotation matrix, 9 dimension, and all angles, 3 dimension, axis angle, 3 dimension, quaternion, 4 dimension, 60 rotation, 6 dimension. These are a little bit advanced, so we will not cover. We will only cover very basic stuff today. Rotation metrics, all angles, and axis angle. And all rotation representations can be transformed to each other. For example, Rodriguez formula is can be used to transform axis angle to rotation metrics. Axis angle to rotation metrics. I mean, we already have mathematically, we can convert each 3D rotation to different representation. And rotation metrics, this is the 2D rotation metrics. We know this is, we learned this high school. And then we now try to expand this to 3D space. So this is 2D rotation metrics, and this is 3D on XY plane, right? And this one shows the rotation metrics in 3D. So we have 3 axes in rotation, in 3D, right? X-axis, Y-axis, and Z-axis. And so that we can rotate about each axis, rotation about X-axis, rotation about Y-axis, rotation about Z-axis. So rotation about X-axis, here, this one. Then we are rotating on the YZ plane, right? This one, YZ plane. And rotation about Y-axis, we are trying to rotation this one. Then we are trying to rotate in XZ space, right? And then rotation about Z-axis, we are now to rotate on XY space, right? XY space. And these represent 3D rotation for each axis. Here, if we rotate on about X-axis, then there's a right-hand rule, and then we can, so the axis rule, the X-axis becomes our thumb, and then we rotate about counterclockwise, so that we can make this kind of YZ axis here, YZ axis. You can just rotate and then rotate it. Then YZ axis, so that here cosine, minus sine, sine, cosine. But if we do rotation about Y-axis, then it's a little bit different. Y-axis, then we need to get XZ plane. But the XZ plane, you can see that this one, XZ plane. You can, if you convert that, then the direction of X is opposite. So that we need to take minus sign here. And rotation about Z-axis, then we have XY. This is just the same rotation matrix of this one. So that we can multiply the different rotation matrices to accumulate rotations. And this shows the Bayesian rotations for each X, Y, and Z axis. So rotation matrix, it is over-parameterized. 9 dimension. We are only interested in 3-dimension space, but rotation matrix, 9-dimensional matrix. So it's over-parameterized, right? So that means not all 9-dimensional matrices are rotation matrices. First, it needs to satisfy orthogonality. R transpose R should equals to identity matrix. That is orthogonal matrix. And right-handed, that of R should be 1. So this two condition is the necessary information condition for the rotation matrix. Only 3x3 matrices that satisfy these two condition becomes rotation matrix. And each column of rotation matrix is a new rotation axis, and each column is a unit vector, and the only unique representation without ambiguity. And this is also important. I introduced there are many 3D rotation representations, but rotation matrix is the only unique representation without any ambiguity. So in case of all angle, this is a very simple example. All angle, this is x, y, z, and let's say x, y, z. We can add just 2 pi 360, right? This is degree. We can add 2 pi, then this rotation and this rotation are the same, but they have different numbers, right? So all angle have, of course, there are many, other representations all have ambiguity, and this one is the most easiest example. We can add 2 pi radian to the degree, then we have, minus 2 pi, minus 2 pi. Then these numbers are different, clearly different numbers, but they represent the same rotation. But so 3D rotation. So there is no one-to-one relation. There are one-to-many relation in other representations. But rotation matrix Always 1-to-1, no ambiguity. But not all matrices are rotation matrices. It needs to satisfy these two conditions. And all angle, let's say we have these numbers. Let's say we have these numbers. It is a little bit hard to understand what is happening in 3D space, right? Let's say we have 3x3 rotation matrix. We humans, it is actually a little bit hard to understand what is happening in 3D space. But all angle is easy. We have 3 angles in 3D space, and then we have yaw, pitch, and roll. This is aircraft, and then roll is, just roll this rotation, and then pitch is this rotation, the yaw is this rotation, and so that is very easy to understand for humans. Let's try this demo. But the one problem is for all angle is that I call it gimbal lock. It's singularity of all angle. So let's try this demo. Okay. I have no idea why this does not work. Okay. Let's now the pitch is set to 90 degree, and yaw and roll are just 0 degree. And as you can see, the blue and green gimbals are overlapped perfectly because we set pitch to 90 degree. The problem is that, as you can see, you now have 2 degree of freedom because the 2 rotation axes are aligned perfectly, so that we no longer have 3 degree of freedom, only 2 degree of freedom. As you can see, the 2 circles are overlapped perfectly, so that there are only 2 circles actually. So if we rotate yaw, if we rotate roll, they rotate in the same direction, right? I'm just changing yaw and roll. Originally, they should move aircraft in a different way. But if we set pitch to 90 degree, then yaw, aircraft is just rotating in this direction, right? Yaw or roll, they're rotating in the same direction. So we only have 2 degree of freedom now. That becomes a problem. That is called gimbal lock, singularity of all angle. So this results when 2 axes are effectively line up, resulting in a loss of degree of freedom. So that originally we have 3 degree of freedom. This is normal situation. The plane can rotate in any directions. The gimbal lock, 2 out of 3 gimbals are in the same plane, so that we only have 2 degree of freedom, unfortunately. You can visit the demo website and then set pitch to 90 degree, and then you can rotate the aircraft by yourself. And you can get that there is some singularity. We only have 2 degree of freedom. Set pitch to 90 degree, and then just change yaw and roll. Then they rotate the aircraft in the same way. That is called gimbal lock, singularity of all angle. So that we need to be very careful when using all angle. Imagine you're controlling the aircraft, but now we only have 2 degree of freedom. With 2 degree of freedom, it is very restricted to control the aircraft in 3D space. So that in such cases, aircraft just can be crushed to some ground, and there can be many dangerous situations. So that when we use all angle, we need to be very careful, and that is the reason why people might not use all angle often, because it might suffer from gimbal lock, singularity. So this is all angle, and axis angle is another representation. So any 3D rotation can be represented by, the axis angle is from this motivation. Any 3D rotation can be represented by a unit vector v, rotation axis, and angle theta, how much you rotate around the axis. Any 3D rotation can be expressed, can be represented by a combination of another unit vector v, some unit vector v, and then an angle theta. So axis angle is from this motivation, so that we represent axis angle as a theta v, 3D vector. V is a unit vector, right? Unit vector, and theta is just a scalar. There are 3D vector whose norm is theta. That is the axis angle, theta v. So it's 3D representation. The axis angle, it also has ambiguities. The first one is that theta v can be decomposed to two things, right? Theta and v, minus theta and minus v. Both represent the same rotation, but they are based on different axis angle, different rotation axis, and different angle, because they have different signs. And also, when theta is equals to pi, then theta v and minus theta v is the same. Rotating an object around this 180 degree, rotating an object around this 180 degree, they gives the same result. So that gives a ambiguity of axis angle. But there's axis angle suffer from ambiguity, but it is compact, and it does not suffer from gimbal lock. So and compact, only 3D, not 40, 60, 90. They're widely used actually. Axis angle is widely used. There are also others, like quaternion 60 rotation. Quaternion is 4D. It extended axis angle perpendicular to 4D space. It's quite widely used actually. Quaternion is very widely used. Slurp is the very famous algorithm to interpolate rotation instead of linear interpolation. And 60 rotation. We are interested in neural network, right? If we use neural network, you need to use 60 rotation. Because rotations are, and 60 rotation is from this paper. Joe was my colleague when I was meta. So rotation is not continuous actually. So you can see this figure. 0, 2 pi. 0 and 2 pi, they represent the same rotation, right? But they have very different number. But it turns out that they represent the same rotation. But the 3D rotation is not continuous. So that if neural network, let's say, neural network outputs 0, but our target is 2 pi. Our GT is 2 pi. This is output, this is GT. Then loss function is very high, right? Loss value is 2 pi. Although the model outputs the correct angle because of the discontinuous of the rotation, loss value could be very high. This kind of thing could happen, so that this paper tries to introduce continuous rotation representation, which is 60. 60 rotation is just the first two rows in rotation matrix. We have rotation matrix. This is 90 degree, right? 90 dimensional representation. 60 rotation is not a special thing. Just we have 9-dimensional rotation matrix. We just select first two row vector of the rotation matrix. That becomes 60 rotation. Using this so that we can use in input and output for neural network, we need to use 60 rotation because it is continuous. These are just advanced ones. But the rotation matrix and all angle, axis angle are very basic stuff and then very widely used. So then I hope you get familiar with this kind of 3D rotation. Very complicated compared to the 2D rotation, like a 2D rotation here. Is it okay? Anything is unclear about the 3D rotation? Actually, this kind of 3D rotation can be used in many places. In robots also, but in computer graphics or animating some virtual characters, or animating any scene or object in computer graphics, all this stuff are based on this kind of 3D rotation representation. And forward inverse kinematics. So we learned the basic stuff for the basic component of robot motion, which is 3D rotation. And using such kind of 3D rotation, we are now trying to move the robots. That is the about forward and inverse kinematics. And let's say we have this kind of robots, and theta is a joint angle, and P and Q are the position and orientation of end effector. End effector is like a end of kinematic chain, like a hand. Forward kinematics takes theta, outputs given joint angle, outputs position, orientation of end effector. That is forward kinematics. Inverse kinematics, opposite. It takes position, orientation of end effector, and compute joint angle. So they say opposite operations. So forward kinematics might not easy to come up with some use case, but the inverse kinematics, for example, if you tell robots, grab this microphone, then the target position is this microphone, right? And there can be some combination of joint angle. For me, I mean, I can grab my bottle in this direction, or in this direction. The same position, but there can be many joint angle of my shoulder and elbow that can reach to the target position, right? There can be many combination of my shoulder and elbow rotation. So inverse kinematics is about that one. Given target position, how can we manipulate robots to achieve that goal? That is about inverse kinematics. So forward kinematics, actually, there's no ambiguity. One-to-one problem, simple 4x4 matrix multiplication in one sentence. Just you can just keep multiplying matrix, that's all. There's no ambiguity, there's no difficulty, there's no challenge. Just, mathematically closed, guaranteed. Forward kinematics, just a matrix multiplication. The inverse kinematics, as I said, given target position, there can be many combination of joint angle that can accomplish the goal. So one-to-n problem, one-to-many problem. Given target position, there can be many solutions. So inverse kinematics is very difficult. Given target position, there can be many combinations of joint angle, and much more ambiguous and more challenging. This shows the example of ambiguous inverse kinematics. The target position is always the same. This position, this position. But as you can see, there can be many combinations of joint angle for these robots to achieve the goal, right? All these robots successfully reach the target position, but along the kinematic chain, the joint angle is very different. They are all joint angles here. This only shows 8 possible combinations of joint angle, but actually there can be much more than 8. So it is very ambiguous inverse kinematics. And for kinematics, to achieve inverse kinematics, you need to understand forward kinematics. Inverse kinematics based on forward kinematics. Forward kinematics, let's study a very basic example. A simple robot arm in 2-dimensional space. This is 2-dimension, not 3D. And we have 2 joints. Here, joint 1, and here, joint 2. Joint angle are known, theta 1, theta 2. And we'd like to compute position of end effector, this one, XE and YE. Our goal is this one. In 2D space, we can know that the position is this one, right? This is just high school math, right? But then, this is just 2D space and 2 joints, very simple example, but how can we get generalizable representation, mathematical generalizable representation? That is about forward kinematics. XE and YE are the position of this end effector. And then we start with the origin, 0, 0. And this is the homogeneous coordinates. So that we have 1 homogeneous coordinates. And T, so we need to find T, matrix T, so that it can convert origin to the target position. If we can get t, then we can just matrix multiplication so that we can get xe and ye. So t is actually consists of these 4 things: rotation theta 1, translation 1, and rotation 2, translation 2. This is the t. And these are just 2D rotations, so that we have 2D rotation matrix here and homogeneous coordinates. Rotation, and this is translation. We know translation matrix looks like this one, right? Rotation matrix, translation matrix, rotation matrix, translation matrix. And theta 1, L1, theta 2, L2. And there can be 2 perspectives to interpret this equation. The first one is body attached coordinate system. So for each joint, there are axes, right? The green one, red one. We have coordinates axis. We have axis for each joint, for each joint, right? So that in a body attached coordinate system, which is equivalent to local coordinate system of the and the effector body. Now I'll start with the rotation 1. So we slightly rotate the red one and then move translation about the L1, and then apply another theta 2 here, and then move theta 2. Now we can get the position of the anti-effector using this t, right? This is the view of body attached coordinate system. And here, as I said, for kinematics, using theta, we'd like to get position and orientation of the end effector. And then we only utilized, this one is just the length of the robot part. Length is fixed, right? Once we design robots, length does not change, so that we can treat as a constant. Then it only takes theta 1, theta 2. Theta 1, theta 2 changes. According to theta 1, theta 2 changes, and this L1, L2 are fixed, they are constant. Theta 1, theta 2 changes. In arbitrary rotation, we can get the position of anti-effector. That is the forward kinematics, right? It only utilizes theta 1 and theta 2. And then we can get anti-effector position. That is the forward kinematics. And another viewpoint is the global coordinate system. We just use the origin global coordinate system. And here, we apply translation first, L2, and then we apply theta 2. And then we move about the L1. So as you can see, the difference is that here, the follow-up operations are done in this space, not green space, red space. In a body attached coordinate system, we apply theta 2 or L2 on this body attached coordinate system, this coordinate system. But global coordinate system, we always apply this kind of theta 1, L1, theta 2, L2 in the green space. Here theta 2 is defined in green space, and the theta 1 is also applied in green space. The global coordinate system, it tries to, mathematically both are correct, but the first one, body attached coordinate system, tries to interpret this equation in a view of body attached coordinate system. There are different coordinate systems, and then the first one tries to interpret this equation for each joint. Each joint has different coordinate system, so that it tries to interpret this equation in a view of body attached coordinate system. And the second perspective, they try to interpret this equation in a global coordinate system, the green one. You can see theta 2, theta 1, always applied on the global coordinate system in the green axis. But here, body attached coordinate system, theta 2 is applied on here, not here, right? In the green axis, no, red axis, not green axis. So that the body attached coordinate system interpretation tries to interpret this equation in a view of body attached coordinate system, while this one tries to interpret this equation in a green axis. But both are correct. I mean, both are correct. And I think it's a little bit hard, but the important thing is that we have kinematic chain. We have kinematic chain here. We have kinematic chain, and then we have rotation, and then we apply rotation and length of the robot parts so that we can get the end of and position of the end effector. That is the goal of forward kinematics. And this kind of forward kinematics is, of course, used in robots, but also used in everywhere in computer graphics, character animation, or object manipulation. All the things are everywhere. Is used in everywhere. Forward kinematics is used in everywhere. And inverse kinematics. As I said, inverse kinematics is the opposite of forward kinematics. So forward kinematics, given theta, we're now trying to get position orientation of end effector. Inverse kinematics, given position orientation of end effector, we like to compute joint angle. That is the goal of inverse kinematics. The typical way for inverse kinematics is optimization. Can you see this pseudocode? This is pseudocode, very simplified code of inverse kinematics. It's very similar, just optimization. We first initialize the joint angle. We initialize theta, and then we have optimizer, and then there's an iteration. We first perform forward kinematics from some initialized theta, and then we have end effector position, right? X is the output of forward kinematics. Forward kinematics is differentiable, so that the entire pipeline is differentiable. We have end position X, and then we have X target. We compute distance, loss function between our forward kinematics output, Fk output, and target position. That becomes loss function, and then we just simply minimize this loss function, and then just repeat this, right? This is a typical way for inverse kinematics. From initialized joint angle, we first perform Fk, and then we get joint position, and then we minimize losses between target and Fk output. We repeat this. There's we did this kind of stuff, right? In neural network, we optimize neural network weights by minimizing loss function. Exactly the same. Fk is just the forward path of the neural network. Then exactly the same. This is the typical way for inverse kinematics. That means we need some iteration. So it might be slow. In this kind of iterative optimization, it might be a little bit slow. And anyway, this is the typical inverse kinematics algorithm. But as you can, maybe some of you guys know the optimization. For the optimization, initialization is very important. So here we initialize data here. But without proper initialization, IK could fail. This shows as I said, humans also have kinematic chain. So all things are applicable to robots and humans. And this shows the IK failure case of human. So the target, here we have target, right? X target. In this example, X target is 2D human key point, not 3D. Let's say, so here we have 2D wrist, elbow, shoulder, wrist, elbow, shoulder, hip, knee, ankle. As you can see, if you project this human, then the 2D key point distance might be very small. Especially this one is left leg, right? Left knee and left ankle. You can see left knee, left ankle, and then here right knee, right ankle, right knee, right ankle. They look, in 2D space, they look good. Oh. Okay. But this is not what we want, right? We cannot do this kind of pose. This is also the same. It looks good in 2D space, front view. And the 2D projection is good, I think. You can see this one and this one. this one and this one look similar, but the problem is that in side view, they look very a little bit weird. So because of depth ambiguity, IK with 2D requires careful initialization. If we just randomly initialize like a T-pose human, then we can get this kind of weird examples. So that optimization, initialization is very important, but just random initialization or just T-pose initialization, it might not give very good outputs because of depth ambiguity. And this problem actually called third-human pose estimation. Given only 2D information, how can we get a combination of joint tangle, human joint tangle, that can explain the input image? That is the 3D-human pose estimation. And there's high overlap between robots and human, right? Robots, we're also interested in IK and getting joint angle for the target position. Human actually is the same. Anyway, and for this specific task, 3D pose estimation, people often, one way is to regress 3D human pose with neural network without iterative IK. Let's say we have, instead of using this kind of iterative optimization, we can get theta equals to model image, right? We can get this kind of neural network so that we do not have to do initialization, iterative optimization. We can skip all this kind of stuff using neural network. That is the, of course, dominant approach. But back in the day, people used to try this kind of iterative optimization approach. Or in some cases, still this kind of optimization is necessary. For example, this is human, but let's say we only have 3-finger robots. We have only 3-finger robots. And there is no pre-trained neural network for 3-finger robot pose estimation. Then how can we do that? Just iterative IK, that is the one way we can do. If there is no pre-trained neural network for 3-finger robots, then we can just, the only solution that we can choose is just this kind of IK approach. So that we need to carefully initialize theta before performing IK, so that people often use network's output for the initialization of IK. If we have some pre-trained weights, if we have pre-trained neural network, then we can use that neural network's output as initialization and perform further refine the neural network's output by performing IK. That is the one typical way. Actually, there are many complicated stuff that I did not introduce, but we cannot cover all details given limited time. So we cover very basic stuff for robots and kinematics and 3D rotation. It's good. Anything is unclear? Any question about the kinematics? Good. So next time we will cover